On this page of notes, we're going to start an explanation of a mathematical operator called the gradient. So the gradient and its mathematical definition and manipulation is not needed for our course. You will not be tested on it either in our class or for the AP test. But to really understand our previous equation, the fact that the electric field is negative the derivative of the voltage with respect to x, and then we have the x hat here to really get a better understanding of that equation within physics and why it is that it explains that the electric field is perpendicular to those voltage lines and that the electric field always points from a higher voltage to a lower voltage, so a maximum decrease of the voltage is really understood by this gradient operator. So let's start this. Well, from calculus, we know that a derivative, ordinary derivative, is dx dt, where that equals the slope of the tangent to the function x of t. It also equals the rate of change of x, the instantaneous rate of change of x with respect to t. So that we know from calculus, and that is called an ordinary derivative. For us, it's the only derivative we've probably covered at this point. But the other thing you probably have not been exposed to in calculus is this notion of differential calculus, and the fact that we can take the dx and the dt and separate them out as really these differential elements. And when we do that, we can see by chain rule, by cancellation, that dx equals this term, which we have bracketed dx dt, times dt, and then we can understand that dx dt term as the proportionality factor, right? That describes how much dx we get from a given dt. So in a given time increment dt, how much change do we get? Dx, well, we get dx dt. That's our proportionality factor. Well, the gradient is understood by looking at how, or one way to understand what the gradient will show us is to look at how these voltage lines will correspond to specific changes as we move in space. So what we are looking at here is that, for example, if we start at a voltage, whatever V2 is, so it doesn't matter the value, but we're going to start at that voltage. If we are going to move off that voltage line, how would our voltage change? Well, as it says here, and hopefully that's understandable, that there's an infinite number of ways to change the voltage, right? We could go anywhere in space three-dimensionally, and the voltage would change based on that movement. However, in order to maximize my change in voltage, I must move perpendicular to the voltage line to get to the next line. So there's only one way to get a maximum increase or maximum decrease. The most efficient way, the only maximum change, is this perpendicular. Now, the example I've chosen is, of course, for the uniform, but we will see it corresponds for other shaped equipotential lines and surfaces. So the voltage itself is a scalar, as it says here. So we have a scalar value based on any position x, y, z. So any point we are at, as long as we know the x, y, and z, if we have a mathematical expression for the voltage, we would get an actual voltage value at that point in space. And then just like we considered the proportionality factor in the x, if we do that individually for the y and the z, our derivatives, right, those ordinary derivatives, so which again for us was the only derivatives, now become partial derivatives. So the d's kind of become sloppy 2's, right? So it becomes this kind of swoopy d, and that lets us know it's a partial derivative, which means it's still the proportionality factor between how much does v change, right, when x changes. That will be the proportionality factor that tells us the change in v from x, but we can do the same thing, the change in v from y is based on that proportionality factor and is based on this proportionality factor. So those derivatives are taken the same way you would take any derivative, but as you'll see, any other variables that are in the equation are ignored, and by ignoring them, we just hold them as constants, and we'll see more about that on our next page of notes. So get these annotations down. It's beginning to understand the gradient, and we're going to finish this up in our next lesson.